All right, ladies and gentlemen, today we're going to be learning about two things, something called homologous series in organic chemistry, and then something else called isomers. So those are our two big points in this particular lecture, homologous series and isomers. So getting started with homologous series, first of all, what are they? Homologous series, by definition, are a group of compounds that are all either alkanes, alkenes, or alkynes. Now, think about this word homologous. It has this prefix, homo, that we've seen before. You've seen this prefix before. And you should remember that homo means the same. Hetero means different, homo means the same. So homologous series is simply multiple compounds that have something in common. And the thing that they have in common are the bonding. That the bonding is all alkanes, meaning single bonds. Right? Remember, alkane, that ane suffix means single bonds. Or the bonding involves double bonds, so that's what's the same between them, they all have double bonds. Or bonding involves triple bonds. So homologous series simply means all alkanes, all alkenes, or all alkynes. And you'll notice that in your reference table, that table that has the general formulas for alkanes, alkenes, and alkynes is actually titled homologous series. Now, homologous series, this group that's either all alkanes, all alkenes, or all alkynes, they can be either saturated or unsaturated. A saturated hydrocarbon is actually, by definition, an alkane. A saturated hydrocarbon is a hydrocarbon that has all single bonds. Now, what does saturated mean? We've seen this word before. We saw it when we were talking about liquids and solutions. Saturated, hopefully you remember that, it means full. In the context of solutions, it means that you can't dissolve any additional solute, that the solvent has taken in all the solute that it can hold, so that if the solution is quote-unquote full of solute. In the case of hydrocarbons, we're not talking about solute and solvent anymore, but what we are talking about are hydrogens. If your carbon chain is all single bonded, it means that you have the maximum amount of hydrogens connected to the carbons that you possibly can. In order to have a double bond or triple bond, you actually remove hydrogens from your hydrocarbon. So a saturated hydrocarbon has all single bonds. Saturated hydrocarbon, all single bonds. Saturated, nothing but single bonds. So that's our alkane series. So alkanes, we can say that they are also considered saturated hydrocarbons. They're essentially saying the exact same thing. Unsaturated hydrocarbons, well, unsaturated means not full. Unsaturated hydrocarbons are both alkenes and alkynes. So any hydrocarbon chain that contains at least one double or at least one triple bond. It can be either. Now, it's called unsaturated, meaning it's not full. And in this case, it is not full of hydrogen. It is possible that you could have more hydrogens connected to those carbons. And if you've heard the term saturated and unsaturated fats, it is actually to this idea of hydrocarbons that's referring. A saturated fat is a fat in which the carbon chain is connected totally with single bonds, meaning it has the maximum amount of hydrogens attached to the fat. An unsaturated fat contains at least one double or at least one triple bond in it, meaning it does not have the maximum amount of hydrogens. So when you hear this word saturated versus unsaturated fat, that's actually referring to the amount of hydrogens that are attached to the hydrocarbon portion of the fat molecule. So saturated single bonds, that's the really important part of these terms, saturated single bonds. And what we can do with this is this chart right here. Now, you're going to need your reference table for this. And you're going to need that portion of your reference table that talks about alkenes, alkenes, alkynes, and has the general formulas for them. Because we can analyze a formula to figure out which homologous series it belongs to, meaning is it an alkane, alkene, or alkyne, and determine if it's saturated or unsaturated. So you should have your reference table open. I can't remember if it's table Q, but it's the one that talks about alkanes, alkenes, alkynes. And the ane suffix, alkanes, right, remember the general formula that's there in the reference table, CnH2n plus 2. versus alkene. That's the general formula of CnH2n. And alkyne is the general formula of CnH2n minus 2. So looking at this first formula right here, C3H8, we're looking to see which of these patterns it fits into. And it's all based on the number of carbons. This has 3 carbons, but 8 hydrogens. So the number of hydrogens is double that of the carbons plus 2. So 3 times 2 is 6, plus 2 is 8. So this fits with the CnH2n plus 2 pattern. Which means, I'm actually going to go to the homologous series one, that because it fits C2n to H2n plus 2, that this is an alkane. And alkanes, saturated or unsaturated, are always, by definition, saturated. So we know that that is a saturated hydrocarbon because it's an alkane. Now, for naming this, we're going to do, this is a two-step process. The first step is looking at the number of carbons. That gives us our prefix. And then the suffix is looking at the bonding. So, the number of carbons in this, there are 3 carbons, so the prefix is going to be pro. That means 3 carbons. Now, the bonding actually refers to the homologous series. Which homologous series is it? Well, it's an alkane. So I'm going to use that ane suffix here. And that compound is propane. Didn't even need to see the bonding. Didn't need to see it drawn out. I utilized the fact that it fits the CnH2n plus 2 pattern to get the suffix that I needed, and simply the number of carbons in the formula to get the prefix that I needed. So the next one, C7H12. Again, I'm going to start by looking up here at the different patterns. Which pattern does this formula fit into? Because that's going to help me get from the name, homologous series, and whether or not it's saturated or unsaturated. So C7H12, see, it's got 7 carbons. So if I double that, that's 14. But that's not how many hydrogens I have. I actually have 2 less. So that actually means it's going to fit the CnH2n minus 2 pattern, which is an alkyne. Filling that in the homologous series. Now, alkynes are unsaturated. Only single bonds are saturated. An alkyne is a triple bond, so it's unsaturated. Now I'm going to go back to the name. And again, the name is based on the number of carbons first, and then the bonding is second. So there are 7 carbons in this. So the prefix is hept for 7 carbons. And then I want to use the suffix for the bonding, which again, this is an alkyne, so the suffix is going to be on. So then this is heptyne. That's heptyne. You can tell without even having to look at the bonding based on the pattern I did. And the last one, C5H10. Again, looking at our patterns, it says 5 carbons, double 5, 5 times 2 is 10. That is precisely the number of hydrogens we have, so this fits with the CnH2n pattern, which means that is an alkene. That's the pattern for alkenes. And again, both double and triple bonds are unsaturated. So alkenes and alkynes are unsaturated, only alkenes are saturated. And then looking at the name of this, number of carbons, that's going to come first. It says 5 carbons. The prefix for 5 carbons is pent. And then the suffix is based on the bonding. The bonding is what the homologous series is telling you. So this is an alkene, therefore the suffix is going to be ene. So this is pent. Then the next topic for today is something called isomers. Isomers are an important concept in organic chemistry because we have all this stuff where we can draw compounds and we can show the bonding, and sometimes, absolutely sometimes, we have compounds that have the exact same molecular formula but different structural formulas. And we call those compounds isomers. Now we're going to talk about what does that mean. What do you mean, same molecular formula and different structural formulas? But the first thing that I want to point out is that we've seen this prefix, iso, before. We've seen it when we're talking about isotopes. We talked about isotopes back when we did atomic structure. Isotopes are atoms that have they're the same element, meaning they have the same number of protons, but they have different number of neutrons. They have different mass number. Same element, different mass number. Same number of protons, different number of neutrons. If you look at this definition of isomer, compounds with the same molecular formula but different structural formulas, and you think about that definition of isotope, atoms with the same number of protons but different number of neutrons, you'll notice that they absolutely have something in common in terms of that definition. And in fact, that iso prefix means same but different. And I like to think of that iso prefix as sort of saying that's like a sibling, meaning you have a lot in common with your sibling. You share genetics, you might share parents, you might share the same household, but you are absolutely different people. So you have something that's the same, but also something that's different between you. And that's what iso means, same but different. In the context of organic chemistry, isomer, what's the same between isomers? Same molecular formula. Well, what does that mean, right? Same molecular formula. What does that mean? Molecular formula simply means the same number and type of atom. Molecular formula, that's just when you say how many of each element there are. H2O is a molecular formula. This is 2 hydrogens and 1 oxygen. So just as an example, we might have 2 compounds that are C2H6O and C2H6O. Same number and type of each element. So these could be considered isomers. They each have 2 carbons, 6 hydrogens, and 1 oxygen. Same number and type of each element. What's different then between the isomers? Well, as it says in this definition, different structural formulas. What does that mean, different structural formulas? It means a different arrangement of the atoms, a different bonding, that the atoms are not bonded the same way. Yeah, you have the same number of each type of atom, but maybe they're connected in different ways. So this C2H6O, I actually have 2 ways that I can connect the 2 carbons, 6 hydrogens, and 1 oxygen. I could do 2 carbons bonded to each other, and then an oxygen at the end, and then 1, 2, 3, 4, 5, 6 hydrogens. Or I could do a carbon, then an oxygen, then a carbon, and then do 1, 2, 3, 4, 5, 6 hydrogens. They have the exact same number of each type of element, 2 carbons, 6 hydrogens, 1 oxygen, but they are bonded differently. They are connected in a different order. In one of them, the 2 carbons are bonded to one another. In the second one, the 2 carbons are not bonded to one another. They're bonded to an oxygen. So they're the same, because they got the same number and type of atom, but they're different because they're connected differently. So these are isomers. Isomers, that's what it means. Compounds that have the same number and type of atom, but different structural formula, different bonding between the atoms. So you can put your pencils down for a moment. Not all compounds, you don't need to take notes on this, not all compounds in organic chemistry can have isomers. You actually need a sort of a minimum number of atoms in the compound in order to start to get different arrangements. For example, there's only one possible way. You have methane, CH4, that you can connect 1 carbon and 4 hydrogens. You only have one possible option. If you have 2 carbons and 6 hydrogens, there's only one possible way to connect them. And that's what this is showing. You have one C and 4 H's. This is the only way that they can possibly be connected. If you have 2 carbons and 6 hydrogens, this is the only way that they can be connected. I mean, remember, with methane, even if you write it like this, with your carbons going vertically instead of horizontally, it's the exact same compound as this. You haven't changed it, so what if you write it as a 90 degree angle? Still 2 carbons connected to one another. Likewise, propane, 3 carbons. There is only one way that you can possibly write 3 carbons and 8 hydrogens. You can only write it like this. Even if I did this, remember the longest chain is still a connected carbon is still 3 in a row. That is not any different. And if I were to just write it up in a straight line vertically, that would still be exactly the same. So I cannot With 3 carbons, there's only one way to arrange them. However, as soon as you get to 4, as soon as you get to 4 carbons, that's really the tipping point where you can start to have different arrangements of carbons. With 4 carbons, you have 2 possibilities: 4 carbons and 2 hydrogens. First of all, you can put your 4 carbons in a row, so connect them all in a straight line, a linear alkene. Or you can start to have branching. So instead of your longest chain being 4, now your longest chain could be a little bit shorter, it could be 3. And you could have that 4th carbon, instead of being connected in a straight line, have it be a branch, have it be a substituent, have it be an alkyl. So these would be the 2 isomers for C4H10. So 4 carbons and 10 hydrogens. Again, this is just showing it. You don't need to take notes on this. I can put the 4 carbons in a straight row. This would be butane. Or I could put 3 carbons in a row with 1 carbon as a substituent. And this would be 2-methyl propane. So they are bonded differently. Each of them has 4 carbons and 10 hydrogens. But I could either put those 4 carbons along a straight chain, or I could put fewer carbons in a straight chain, 3 carbons in a straight chain. I could put one of them in the middle of the chain and have it be a substituent instead. So 4 is really the minimum number of carbons that you need in order to start to get a carbon-based isomer. You have to have a minimum number of atoms in order to start to have different arrangements, different bondings for them. So pencil back up. What I have in this chart, this is actually the C2H6O and the C2H6O that we were looking at before. So these are the 2 different arrangements of it. Again, with the OH on the end versus the oxygen in the middle. What else is different between isomers? Because having the structural formula be different actually leads to many, many other differences as well. And looking at this chart, boiling point, melting point, physiological activity. Boiling points of these 2 different compounds. One is 78.5 degrees Celsius and one is minus 23 degrees Celsius. They are entirely different boiling points. Ditto for the melting points. Minus 117 versus minus 138. Very, very different melting points. Having different bonding leads to different physical and chemical properties. These 2 compounds, even though they each have 2 carbons, 6 hydrogens, and 1 oxygen, because they are bonded differently, they basically are totally, totally different compounds from one another, and they behave completely differently. The first one, ethyl alcohol, that's ethanol. That's the alcohol that's in wine and beer and liquor. That's a compound that basically depresses your nervous system, impairs your judgment, makes everything get a little foggy and a little hazy. Versus the other one, dimethyl ether, that's an anesthetic. That stuff knocks you out. Like, people used to breathe in ether for fun. It would be like drugs they would take at parties and they'd just all pass out. But it has a completely opposite effect on your system. Like, it's an anesthetic. You breathe it in and you go to sleep, like, right away. So, totally different physical and chemical properties between isomers. Which means that different isomers are going to have different melting points, they're going to have different boiling points, and they're going to have different effects on the body. That's what physiological effects mean. Different chemical reactivities. One of these is an alcohol. Alcohols react in predictable ways that are very, very different to the ways that ethers react, which is the other type of compound. So different bonding leads to different properties, both physical properties and chemical properties. They have different structures, so they will react differently from one another. The only thing they have in common is the number and type of each atom. 2 carbons, 6 hydrogens, 1 oxygen. Their bonding is different though, which means that all their properties are going to be different. So we're going to practice a little bit with isomers, drawing isomers. So the first step, draw possible structural isomers for C4H10. If you're ever asked to draw isomers, you really want to think about two possibilities. Number one, putting all of the carbons just in a straight line from one another, straight chain. That's always going to be one possibility. So with 4 carbons and 10 hydrogens, I can go 1, 2, 3, 4 carbons, put them all in a row, and then the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all of my carbons are in 4 bonds total, and I have like 10 hydrogens. Now for the isomer, you no longer want to think about putting 4 carbons in a row. And remember, you don't want to do this, 1, 2, 3, 4, because remember this is exactly the same thing as that, right? So what if you wrote the last one up? It's still a chain of 4 connected carbons in a row, right? This is the chain of 4 in a row. So it's the same compound. Instead, what you want to start to think of is saying, instead of 4 carbons in a row, let's make it fewer carbons in a row. Let's make it 3 carbons in a row. 1, 2, 3. And let's put that 4th carbon in the middle. Because now the longest chain of connected carbons is still 3. And you have a substituent. And then going in and giving each carbon 4 bonds gives me the 10 hydrogens that are connected. So these would be the 2 structural isomers. And there are only 2. Remember, if you were to draw 1, 2, 3, and then the last one coming down, it's exactly the same thing as this one. Right? It doesn't matter what number down, it's actually the exact same compound. So this doesn't count as an additional isomer. You really just have these 2 isomers, and that's it. Now, C5H12. The first isomer that you should draw should be all 5 carbons in a row. So that's draw all possible structural isomers for C5H12. So we got that as we go. Okay, let's go 1, 2, 3, 4, 5, and then give each carbon 4 bonds. This is one of them. So a chain of 5 connected carbons right in a row. Then start thinking about making the longest chain shorter. So start thinking of going 4 carbons in a row. 1, 2, 3, 4. But you have to have that 5th carbon. So put that 5th carbon not on the end, but somewhere in the middle. So I can put it here. And then go ahead and give each of those carbons 4 bonds. There's only one more possible structural isomer for C5H12. There's actually only 3 in total. But before we talk about the third, I want to point out that the second isomer here, you can also draw it like this. 1, 2, 3, 4. And put the 5th carbon at this position. But recall that both of the methyl groups in this, I would number this carbon chain 1, 2, 3, 4, so that the substituent is closest to the number 1 carbon. I number this carbon chain in the opposite direction, 1, 2, 3, 4, so that once again, the substituent is closest to the number 1 carbon. This is not a different isomer. This is exactly the same structure as this one. I mean, it is exactly the same thing. They are both 2-methylbutane. So that this one over here does not count as an additional isomer. It is the exact same compound. So because I can't count that as a different isomer, I now have to start thinking about shortening my carbon chain again. So in the first one we had 5 carbons in a row with no substituents. Then we had 4 carbons in a row with 1 substituent. So maybe we could do 3 carbons in a row with 2 substituents. Now with substituents on a 3-carbon chain, I cannot put them on the end. If I put the substituents on the end, I would be lengthening my carbon chain to 4 carbons. I don't want to do that. I want to keep my carbon chain at 3. So I could put one of my substituents up there and one of my substituents up there. And that is the third possible structural isomer for C5H12. So this first one, again, 5-carbon chain with 0 substituents. The second one is a 4-carbon chain with 1 substituent. The last one is a 3-carbon chain with 2 substituents. So all of these have the same number and type of each atom, but they have different bonding for each one, different bonding. So draw the structural formula for 2-chloropentane and draw at least 2 structural isomers of 2-chloropentane. This is a two-part question. Basically saying, hey, we have this compound 2-chloropentane. Think about that first, and then let's draw some isomers for it. So 2-chloropentane, drawing 2-chloropentane. Again, we want to start at the back. So pent, that means 5. So I'm going to draw 5 carbons. 1, 2, 3, 4, 5. Ane means single bonds, so I already have them connected via single bonds, so that's all set. Chloro, that means Cl, and it's telling me to put the chlorine on the number 2 carbon. So, okay, I'll put the chlorine on the number 2 carbon, and then go ahead and take every carbon 4 bonds. Remember, halogens only make 1 bond. They have 7 valence electrons. You only need 1 additional electron to get to 8. So, unlike carbon, which is 4 valence electrons, needs to make 4 bonds. Halogens only need to make 1 bond. So there we go. That's 2-chloropentane. And then the question says, draw at least 2 structural isomers of 2-chloropentane. There are actually many different structural isomers for 2-chloropentane. So we only need to draw 2 of them. Possibilities, things that we could do. Well, 2-chloropentane has a chain of 5 carbons. So one way that we could change this, but still keep the same number of C's, H's, and the Cl, is to now, instead of having a chain of 5 carbons, I could have a chain of 4 carbons. So I could go 1, 2, 3, 4. But I still need that 5th carbon, otherwise it's not isomer. It has to have the exact same number of carbons in it. But I could put that 5th carbon maybe there, as a substituent instead of part of the carbon chain. And then I can keep the chlorine, and then keep the H's. So that works. That's a structural isomer for 2-chloropentane. Another way that I could approach this is I could actually keep the carbon chain. I could keep the 5 carbons in a row. 1, 2, 3, 4, 5. But I want to change the bonding. I want to change the order in which they're connected. Well, I'm keeping the 5 carbons, which means I could instead alter the 2-chloro. I could change where the chlorine is. Because in 2-chloropentane, the chlorine is connected to the number 2 carbon. I could instead have it connected to the number 1. I've changed the bonding. I've altered where the chlorine is bonded to the carbon chain. And that counts as an isomer as well. There are many different ways that we can do this. So what I'm showing you here, these are not the only possibilities. We could put the chlorine on the number 3 carbon. I could have a 3 carbon chain with 2 carbon substituents and the chlorine substituent. I could, in this one here, I could put the chlorine on the number 1 carbon. I could put the chlorine, I could move the chlorine to different positions. So there are actually many possible ways to draw this. These are just 2 possibilities that I'm showing you. Isomers and names. Just a sort of quick comment about isomers and names. The 2 compounds have the exact same name. So if you're examining a compound and you're numbering your carbon chain either left to right or right to left based on where the substituent is, and you realize that the substituent is actually in the exact same position, it's just that they sort of flipped it around, they're not isomers, they're just the same compound. So my sort of default is, if you're not sure if 2 compounds are isomers of one another and you have a structural formula, name them. If they get the exact same name, then they're not isomers. They're just the same thing, drawn slightly different ways. But if they get different names, then they are isomers, and they have the same if they have the same number of type and type of each atom. Of course. So there's the thing about naming. If we know that there's different possible ways to draw things that have the exact same name, you could draw, your carbon chain right to left or left to right. So sort of you always be thinking about that. Lastly, the reasons will try to trick you when it comes to isomers. They're going to try to trick you, and this is a sort of a classic question that they will ask you. They'll say, which is an isomer of the following compound? And they're talking about this compound right here. This compound right here. This compound right here that has a 3 carbon chain with a bromine attached at the number 1 carbon. Right. So that's 1 bromopropane. Which of the following is an isomer effect? Many of these options are designed to make you fail. So we want to be aware of that. The first option here, this is not the isomer of this. Because we still have a 3-carbon chain. And where is the bromine attached? It is still attached at the number 1 carbon. Who cares that it's going down instead of going off to the left? The bromine is still attached to the number 1 carbon. That is not isomer. It is the exact same compound. There is nothing different about this compound. It is not an isomer. Next up, choice 2. Okay, we have our 3-carbon chain. But then we have a bromine that's attached to number 1 carbon and a bromine that's attached to the number 3 carbon. This is not an isomer. It does not have the same number and type of each atom. Our thing only has 1 bromine here. An isomer that cannot have 2. It has to have the exact same number and type of each atom. The third one is possibly the trickiest of all. This is not the isomer. But you're saying, hey, well, this is Julian. It has 3-carbon chain. I agree. And you're saying, hey, this is Julian. And there's bromine coming off of the last carbon. So in the first one, we've got our bromine coming off of the first carbon. In this one, I've got the bromine coming off the last carbon. Isn't that the isomer? Because it's bonded in a different place. No! No, it is not! We do not number our carbon chains left to right all the time. We number our carbon chains so that the substituent is closest to the number 1 carbon. If our substituent is on the right, then we number our carbon chains right to left. 1, 2, 3. So this one is actually the exact same compound as the one that is being asked about. It has the bromine attached to the number 1 carbon. It is not different in any way. They just drew it differently. It's the exact same compound. The reason I'm trying to trick you by doing that right there, by writing that bromine attached to the quote-unquote last carbon, but you're going to be smarter than that, and you're going to say, no, it's actually attached to the first carbon. The last one is the isomer. Because the last one has the 3-carbon chain, so 3 carbons. That needs to match. It only has 1 bromine. That's good. That needs to match. But now the bromine is attached to the number 2 carbon. So I have 1 bromopropane in the given, and this is 2 bromopropane. The exact same number and type of each element, but it's bonded the bromine in a different position. The bromine is now attached to the number 2 carbon versus the bromine being attached to the number 1 carbon. So that one's the isomer. Isomer, same number and type of each atom, but different bonding, different structural formulas, and as such, will have totally different properties.